Alright, last video, a little bit of everything today. We're going to go across the entire semester, do section 1, section 2, section 3, section 4. I made section 4 about 40% of the video. You should be familiar with all this, but I think this is all really good stuff that you may see on your final, so let's get it. Alright, so first one we're going to do is this one is section 1 problem. So we've got a car traveling with a uniform speed of 81 meters per second, flies by a state trooper. State trooper sitting on the side of the road. After 2 seconds, the state trooper chases after the car. He catches the speeder 24 seconds after he begins his chase. Determine each of the following. So we want to know his acceleration and his displacement. And then essentially we've got how far have the two traveled in 24 seconds. That's their displacement after 2 seconds, 24 seconds. So this one's not the toughest for you guys in theory because you've done it a million times and you've worked with these concepts for a bit now. If you go back in your mind, you will initially think that this is a kinematics equation problem. So we've got the kinematic equations over here. So let's see, let's write down what we have first. We've got speed or velocity is going to be the 81 meters per second for the car. And he's got a constant velocity, a uniform velocity. Flies by a state trooper. The state trooper is sitting on the side of the road, so I guess we could say his initial velocity is 0, right? I'm sort of thinking ahead here. After 2 seconds, the state trooper chases after the car, so time is going to be 2 seconds, or I guess maybe not time, but we're going to write time as 2 seconds just to consider for a second. If he catches a speeder 24 seconds after he begins his chase, determine each of the following. So we want to know if he catches his speeder in 24 seconds. Catches a speeder in 24 seconds. What is his velocity? Or what is the acceleration rather? So let's see, I'll show you what I have written down so far. So we've got V1, which I said is the car, 81 meters per second, and he goes 2 seconds before the cop starts chasing him. Cop's initially at rest, so 0, and the cop catches him in 24 seconds. So 24 seconds, what's the scenario? At 24 seconds, they should be at the exact same location, right? So you can set displacement 1 to displacement 2. They should have the same displacement after the 24 seconds. We want to know what the acceleration is. I'll write that up here as well. The little A equals question mark. You know what that means. So that's the idea. The speeder is going to catch, or the cop's going to catch up to the speeder in 24 seconds, and they're going to have the same displacement. So take a second to look at what equation you want to use. I'm not going to show you my setup. I'll let you take your time to do your setup, and we can meet at that point. So should have got something by now. Here's what I've got. I just set 2 displacement equations equal to each other. We've got 1 for the car and 2 for the cop, right? So let's start with the speeder, right? His initial displacement is going to be what? We've got constant 81 meters per second, and we've got the time equals 2 seconds, right? He travels 2 seconds before the cop starts chasing him, so what's his initial displacement? And it would be the 81 times 2, right? We've got displacement equals velocity times time. So I'll show you that. But you guys should know that displacement equals velocity times time. And we can just plug in the 81 times 2 for the initial displacement of the speeder. That should be 162. V naught t is going to be the initial velocity times the time. Initial velocity is going to be 81, and the time is going to be 24. So 81 times 24. And then 1/2 acceleration times time squared. What's the acceleration for the speeder here? And you should think to yourself, if he's got a constant velocity, no acceleration, so we're going to say 0 for that. So for the first part of our equation, we're going to have 162 plus 81 times 24. That will give us the displacement of the speeder and also of the cop. So I guess we could actually go ahead and solve for part B. We're not going to do that yet. We're going to find the acceleration first. So for the second part of the equation, we've got x naught, or the displacement initially for the cop, and the cop starts at the 0 point. So his initial displacement is going to be 0. So that's easy. For his velocity times time, velocity is going to be 0 here because or initial velocity rather is going to be 0 because he starts at rest, right? He's initially sitting and the guy speeds past him and then he starts accelerating after him. So his initial velocity is going to be 0. And then, appreciate it. And then acceleration is what we're finding. So we're going to do plus 1/2 acceleration, which we don't know. Time, which we know is 24 squared. So 1/2 at squared. So we've got 1/2 a 24 squared. I know it's really bad, I'm realizing, but that's squared, 24 squared. So we've got 162 plus 81 times 24 equals 1/2 a times 24 squared. So we can erase these zeros, make this look prettier. And our final equation is going to be 162 plus 81 times 24 equals 1/2 times acceleration times 24 squared. Take your time to do this by yourself. You should be good with the algebra by now. I hope you can do this by yourself. But yeah, we'll just meet with the answer, right? So for my acceleration, I'm getting 7.3125 meters per second squared. Make sure you know your units. Acceleration is going to be meters per second squared. And that is part A. Part B, I told you we could already have found it essentially. So let's just erase a bit. Actually, you should be able to find it yourself. So I'm going to let you find it. We can meet with the answers for that as well. And it should be pretty straightforward for you guys. I already alluded to it earlier, so hopefully you were listening, right? And for my displacement, I'm getting 2106, 2,106 meters. So not difficult at all there. And this is where we started from, right? So it's good to remember these things, and it's good to review them for the final, right? So let's get to the next one. So here we've got two-dimensional motion problem. Last one was one-dimensional. This one, two-dimensional. We've got x X motion and we've got a little Y motion. So we've got a jet plane traveling horizontally at 100 meters per second, drops a rocket from a high altitude. The rocket immediately fires its engines, accelerates 20 meters per second squared in the X direction. After the rocket has fallen 1 kilometer, find the magnitude and the direction of the velocity. So we've got a jet plane horizontally 100 meters per second, so our X to velocity is 100 meters per second. Probably should have asked you that, but it doesn't matter. Velocity initially in the X direction is the X, or is 100 meters per second, and then the rock, it immediately fires its engines and accelerates 20 meters per second in the X direction. So its X acceleration is going to be 20 meters per second. So we've got that as well. After the rocket has fallen 1 kilometer, so we've got a vertical or Y displacement, right? So we've got a Y displacement of 1 kilometer, which is 1,000 meters, which you should know. We're actually going to say it's negative 1,000 meters because it's going down. Just a good idea to set down, and to the left is negative, and up and to the right is positive. As you guys know, blah, blah, find the magnitude and the direction of the velocity. So let's draw this actually. Ooh, so you're going to draw the plane. It's going. It's got the initial velocity. It drops the rocket. Drops the rocket. The rocket keeps that same X velocity, but it gathers a new Y velocity. That works. And yeah, so we've got the X. We've got the X. We've got the acceleration as well. So that's interesting. So that's 20. And then we've got Y velocity, which is 0 in theory, right? But you should know that. Actually, I'll explain a bit more. We've got the acceleration going down, which was always there. So this is the idea. This is what we're dealing with. We've got the plane, it drops the rocket goes to a little acceleration, and it has an acceleration pulling down, right? What is causing the Y acceleration? Gravity, right? So gravity's pulling it down, it's causing an acceleration in that Y direction. So we've got the negative 9.8, which is gravity going down. We know the X acceleration is going to be the 20. So I'll show you that I wrote both of those. I wrote both the accelerations. The velocity is going to be, it's going to keep that 100 meters per second. It's not just going to lose the velocity because it comes out of the plane. So we've got velocity equals 100 meters per second. Right, got all that, and we want to know the magnitude and the direction of the rocket. So let's do that. Shouldn't take too long. Should be familiar with this. Two-dimensional motion. The trick here is you make sure that you keep your X values and your Y values totally separate, but there is one link that connects the two, right? What is that link? What is that link? And you should have said to yourself or to your friend, it's time, right? So it's going to take a certain amount of time for that rocket to fall 1,000 kilometers. Still want to have its X and Y velocity, so we want to find the time it takes to fall to get to that 1,000 kilometers, because then we could say that that's the time it took for it to travel in the X direction as well, right? And we want to find, okay, yeah, that'll totally work. So let's focus on the Y components, right? We've got a Y displacement of negative 1,000. Let's do this. Negative 1,000. Initial Y velocity of what? Zero, right? They don't tell us there's any Y velocity initially. It just sort of falls out of the of the plane, right? So 0 is our initial y velocity, and we know that gravity provides an acceleration of what? Negative 9.8, right? So we've got a displacement, we've got a initial velocity, we've got an acceleration. We want to find time, right? And that's pretty straightforward. So let's go ahead and find that. I'm not gonna show you what I'm using, but you should know. You should be able to find it. We've done this before, we've done it a million times. So let's go ahead and do that. So I've got, I'm not sure if this is really aligns with what I just said, but x equals v naught t plus 1/2 at squared. And I think that's on there. Yep. Well, not really, but it's the shortened version of the displacement equation we used with the last question. So displacement is negative 1,000. Initial velocity is 0, so time doesn't matter with that first part. And then 1/2 acceleration is negative 9.8 times time squared. So that's that blue down there. Got all that information in there. You do a little algebra. I'm not going to help you with the algebra. You should know it at this point. Do all the math there, and we get the time to be 14.3 seconds. 14.3 seconds. So that time is how long it takes for the rocket to fall. And at that time as well, we're going to have how far it traveled to the right, or in the x direction. So 14.3 seconds. Let's write that up here. Now that we know that, we want to find the magnitude and direction of the velocity. So we're still got some steps left, actually. So we travel 14.3 seconds, and we have an x velocity and acceleration, right? So with that information, we could do something similar to what we did in the last question, right? We can use that velocity, that acceleration, that time to find its final velocity, right? Just sort of similar, but not exactly what we did in the last question, but we could find our final velocity, right? So we're going to go x first, come back to the y. So final velocity is going to be initial velocity plus acceleration times time. We've got initial velocity as 100 plus acceleration, which is 20, times the 14.3. Run out of space here. So do the math there. 100 plus 20 is 14.3. I'm getting an x velocity of 386 meters per second. So did all that. Final velocity in the x direction is 386 meters per second. So you can write that at the top. Got that. Let's come back to the y. I don't know why I skipped to the x first. But let's go back to the y now. So we've got the same idea, actually. V final should be V naught initial, or V initial plus acceleration times time. We don't know what V final is, but we know what the initial velocity in the y direction is, right? 0. And acceleration we know is negative 9.8. And time is the 14.3, which we found. a second ago. So it's got all that information. A little math. We get our final velocity in the y direction is going to be negative 140.14. So I'll show you that. All that math down there, right there. So we've got our x velocity, we've got our y velocity. Let's use the color. So let's say that our y velocity is negative 140.14. We want to find the magnitude and the direction of the velocity. So let's show you what we mean, right? Let's erase it a little bit. So we've got the rocket, and we've just found that it's traveling in the x direction 386 meters per second, and it's traveling in the y direction the negative 140.14. So next just do negative 140. Save me some trouble a little bit with the math. So here's what we're dealing with, right? We want the vector, right? We want to put those components together, right? So let's do this little thing. So we want this, right? We want that vector, the purple vector. So let's say that we drew it this way, right? And we're dealing with the triangle now, right? We're just dealing with the triangles, huh? So how would you find, or let's make this a little easier, make this a little clearer, right? A, B, C. So here it is again. A, B, and C. C is our velocity vector. If that's the case, how are we going to find our velocity vector with A and B? Pythagorean theorem, right? So we've got a squared plus b squared equals c squared. We know A is going to be 346. We know B is going to be the 140, negative 140. And C we're looking for, so we're going to do a little Pythagorean theorem and some algebra. And you should know how to do that, so I'm not really going to show you much of this. And for my velocity vector, I'm getting 373 meters per second. So there's that. Final velocity 373 meters per second. We want to find the direction as well. So how do we do that? And I'll show you the picture again. You want to remember your trig rules, right? Let's say we want our direction, which would be that angle between the two vectors, or between the vector and the adjacent component, right? We want to find that angle. How are we going to find that angle? Going to use a little trig, right? SOHCAHTOA. So take your time to do your trig. I'm going to do it myself and then show you guys. Ideally you know it, but maybe you don't. So let's see. So we've got that, and then this was and then we've got so what I've done is this, the inverse tangent of the opposite component over the adjacent component, right? So we did that. If you do the math there, getting negative 19.93 degrees. That's your answer for the direction. So your um, velocity was about 373. Your displacement, or your direction rather, is negative 19.93 degrees. Not too tough. A lot of work there, but I like to say physics is a lot of triangles early on. So make sure you're using your triangle rules or Pythagorean theorem. You know in your trig. Of course, know your motion equations. What else? That's it. Trig, kinematics, triangles, and also make sure you keep x and y separate. Of course, make sure you always keep x's and y's separate. And the one link between the x's and y's is the time, right? So you've got all that, and if you remember all that, you should be good when you see something like this on your final, right? Let's get to the next one. So here we've got a car with mass 1,500 kilograms traveling east at 25 meters per second, collide at an intersection with a 2,500 kilogram car traveling north at a speed of 20 meters per second. We want to find the magnitude and direction of velocity of the wreckage after collision, assuming that the vehicle undergoes perfectly inelastic collision, and assuming that friction between the vehicles and the road can be neglected. So here's what we have down here. We've got the diagram. It's got the car traveling east, and we've got the car traveling north. And we've got the collision, of course, is perfectly inelastic, which means that they are going to stick together. And you see they travel in the northeast direction, so we don't know exactly the angle, but we do know that it's going to be in that general direction, because that's just how it works, right? It makes sense, right? So take some time to write out what we've been given, and that should lead us a little bit. So we've got mass 1, and let's actually, before we do that, let's say that north is positive, east is positive, south is negative, and west is negative, right? Not that that's going to be too relevant to our equation, because we're only going north and east, but it is something to consider. You always want to make sure you're going to say before you start anything, so you start doing any math, any physics, which way is positive, which way is negative. So we've got that. Mass 1 is of the first car. Mass 1 is going to be 1,500 kilograms. Velocity 1 is going to be 25 meters per second east, and we said the east is positive, so I'm just going to say that velocity 1 is going to be 25 meters per second. 25 meters per second. Velocity 2, let's use it. Or mass 2, let's start there. Mass 2 is 2,500 kilograms. Velocity, velocity 2 is going to be 20 meters per second. We want to find the magnitude and the direction of the velocity of the wreckage after the collision. So collide, go northeast, perfectly inelastic, and assuming the friction between the vehicles on the road can be neglected. So that's good information. We're doing a conservation momentum problem, right? Momentum is not going to be lost here. So we've got perfectly inelastic collision. That means all the energy is going to be preserved. We're going to write out the perfectly inelastic collision formula, and we can talk a little bit more after we get it written down. So here's the idea, right? We've got two dimensions, right? We've got two dimensions, right? We've got x and y. And what did I say in the last question? We want to keep the x's and the y's separate, right? So let's write it again for the y components. So we've got m1 v1 plus m2 v2 equals m1 plus m2 times velocity. And that's the idea there. I don't think I showed you this, but here's what we've got. X and Y. Conservation of momentum and an inelastic collision. So that's the idea. We could do the x's first and see what we get, right? We can plug in our values. Mass 1 is 1500. Velocity 1, which is in the x direction, right, is 25, positive 25. Mass 2 is to 2500, but velocity 2 is what? We're looking in x direction, what is velocity 2? 0, right? There's no x velocity for car 2, which is going straight up on our picture. So we've got velocity 2 is 0. Velocity 2 times mass 2 is going to be 0. That's in the x direction. So you got that, put mass 1 and mass 2 together, we should get 4,000. Yeah, 4,000. And that's going to be times the velocity final in the x direction. Here's what we've got. Pretty simple, right? You do the math there, you get the final x velocity. So and I'm getting 9.375 is our velocity in the x direction. Let me double check that actually. Yep, makes a lot of sense. 9.375 is going to be our x velocity. So we've got that. I'll show you. Now we want to get the y velocity, right? So mass 1 times velocity 1. Mass 1 is 1500. Velocity 1 in the y direction is what? So remember, car 1 is going straight east. We're looking at the y velocity, right? Up the north and south velocity. Velocity for car 1 here is similar to the x situation. It's going to be 0. So velocity there is 0. So mass is going to be, doesn't matter, 0. So 0 for that first part. And then mass 2, which is going to be the 2500 times velocity 2, which is going to be the 20. And that is it, all right? Should equal the sum of the two, which would be 4,000 again, times the final velocity, which we've not found yet. And all in all, we'd have this, right? We've got 0 plus 2,500 times 20 equals 4,000 times the final velocity. So not too tough there. We got 2,500 times 20, divided by 4,000. And we're getting the final y velocity, which specifies the y. Final y velocity of 12.5. Let's erase a little bit. Try both of these. V final y is 25, or no, 12.5 rather. And V final x is going to be 9.375. So we've got those two values. And let's actually draw a little diagram. Or actually, let's point to our diagram here, right? X component of velocity is going to be the 9.375. Y component is going to be that 12.5, and you'll see they make a little triangle, right? So we want to find that angle between the triangle, or in the triangle, right? So we want to find the angle, which would be the opposite over the adjacent, right? Or the inverse of that. So inverse tangent, opposite over adjacent, we've got 12.5 over 9.375. Our angle should be 53.1 degrees. So our direction is 3.1. We've got our direction. Let's go ahead and get our magnitude as well. And you see, like I said, we've got another triangle, right? So we've got x component of the triangle being the 9.375. We've got our y component being 12.5. Our magnitude is going to be, we've got A, we've got B. Magnitude is going to be the C, right? We'll do a little Pythagorean theorem. And let's see what we've got. Do a little math there. I'm getting the magnitude of velocity as 15.625 meters per second. So that's what we're dealing with. You should know how to do all that math there. But here's a second to look at it. Make sure you got the same thing. And that is that. So, like I said, triangles, make sure you know your trig, make sure you know your triangle rules. Concentration momentum, pretty straightforward idea. Yeah, that's it. It's easy to look at these sometimes and see where your direction will be, and do the math. It makes sense depending on what you determined before you did any work. Then you're on the right track. So that's it for that one. Let's get to the next one. So you've got 2 packing crates of mass, 15 kilograms of mass, 5 kilograms connected by a light string that passes over a frictionless pulley. The 5 kilogram crate lies on a smooth incline, angle 50 degrees. Find the acceleration of the 5 kilogram crate and find the tension in the string. So what are we going to do here? Let's actually draw our diagram first. And actually, while you're drawing your diagram, go ahead and draw your forces in as well, right? Free body diagram, draw your forces in. So let's do that. So first body. How many forces do we have? Two, right? 2 forces in the first body. So first body is a hanging body. I'll show you my diagram actually. So we've got 2 forces, right? Going up we have what? Tension. And going down we have what? Weight, right? So weight is going to be mass times gravity. And also take the time to write out your Newton's second law. Not actually connected to this, but Newton's second law is what? Similar forces should equal mass times acceleration, right? Exactly right. And we also know that we keep our x and y separate, right? So we're gonna write that twice, right? So I'll show you what I'll be talking about. What is this? So up here, some of the forces in the x direction is mass and acceleration. In the x direction, Thermal force in the y direction is mass times acceleration in the y direction. Mass 1, right? Tension up is positive. Mass or weight down is going to be negative. If that's the case, acceleration down should also be negative. So let's actually do a second law for that first body. A new second law equation for that first body. So you should have gotten tension minus mass 1 times gravity equals negative mass 1 times acceleration, right? Acceleration is negative here because we said that going down is negative. Acceleration is going to be going down, right? So negative acceleration, and we're going to set this. But before we say that, I'm going to tell you the tip for Atlas machine problems is what? What's the trick? What's the idea? And the idea is that there's a connection between the two bodies, or two masses. So there's one tension in the rope, and there's one tension or one acceleration. So the same speed that the tension 1 or the mass 1 is going to have accelerating down, mass 2 is going to have accelerating up. So we're going to have tensions equal to each other, and the accelerations equal to each other. So I wrote that up there. Same tension, same acceleration. So the trick, that was a tip, I guess. The trick was that you would set your Newton's second law equations in terms of tension, right? I'm going to say tension equals, or I guess equal to tension. Tension equals mass 1 times gravity, or the weight, minus mass 1 times acceleration. So that is your tension for the first body, or first mass. Second mass, similar, but a little trickier because we got it on an angle. We got a 50-degree angle. And let's make this totally clear for you guys. So let's actually get this. So it's easy to mess this up, but let's make this totally clear for you. So you want to imagine that on the incline, you just tilted your x and y axes. So you can't see that too clearly. Let me make that a bit clearer. So you've got a new x and y axis, and you see I just tilted it a little bit. That's not exactly parallel, but that's the idea, right? So we've got that in mind. We've tilted the axis. So let's do our new second law equation, right? Let's start with that. Tension going up. We want the x component of the weight, right? Because tension is going in the x direction, solely in the x direction. The weight, you'll see, is sort of in limbo if we look at our axes, right? We want only the x component, right? So let's actually clear this up. Y would be parallel, and x would be perpendicular. Just look at that. I drew a little triangle there. And you'll see that weight is your hypotenuse, right? So weight's your hypotenuse. We've got an x and y component, and we know we've got a 50-degree angle at the bottom of the incline. A little geometry trick is that if that's 50-degree incline, this angle where I put this blue dot is also 50 degrees. So that's a 50-degree angle there in the triangle. And we want the x component of the weight. We know what the weight is, mass times gravity. We've got all that information, so take your time to finish your Newton's second law equation. So you should have gotten it by now. I've written it right here. Tension minus mass 2 times gravity times the sine of 50, which is, if you look at that, the opposite from that angle, 50. And then equals mass 1 or mass 2 times acceleration. And the acceleration is going up the ramp, so the up the ramp is positive. So got all that. And similar to the last math, we want to set this in terms of, or actually equal to tension. So tension equals mass 2 times acceleration plus mass 2 times gravity times sine 50. Show that as well. So we've got that little bit of information. We want to find the acceleration. So let's do that. How are we going to do that, do we think? If you set the two equations equal to each other, removing tension, you were exactly right. So we're going to say that tension 1 equals tension 2. So mass 1g, let's move this around. Mass 1g equals, or mass 1g minus mass 1a equals mass 2a plus mass 2g sine 50. I just moved that tension equation to equal this tension equation. So I'm not sure how clear that was, but the idea is you're going to set your tensions equal to each other and solve for acceleration. We've got all our values that we need, so we can plug those in. We've got, let's make some more space. We've got mass 1, which is 15. Gravity, which we know is 9.8. We're going to use positive 9.8 minus mass 1, mass 1a. Wrote this sort of funny. Minus mass 1a, which is going to be minus 15 times a, which we don't know just yet, equals, let's make it split. Minus mass 1a equals mass 2a, which is mass 2 is going to be the 5 kilograms, plus mass 2g times sine 50. So here's what we've got right there in the middle. That's the equation with all the numbers put in. We're going to solve for a, so let's get all the a's on one side. So move a's over. Let's move the other stuff over as well. We've got the constants, so we've got so broken down, we've got 184.54 equals 28. 184.54 divided by 20. Acceleration we're going to have is 9.23 meters per second squared. So not too tough there. Not too tough there. Let's double check our answer actually. Was just like a little bit of a setup type deal, right? So we can erase that. Maybe acceleration. But we've got mass 1g minus mass 1a equals mass 2a plus mass 2g sine 50. So I just rewrote the whole thing. There it is. Rewrote it. A's by themselves, we're going to leave all the variables by themselves, not going to change anything. So we've got mass 2a plus mass 1a equals mass 1g minus mass 2g sine 50. So just rearranged a little bit. There it is on that second row. Rearranged a little bit. Sorry for my bad handwriting, but it's mass 1g minus mass 2g sine 50 equals mass 2a plus mass 1a. We've got the a's on one side, so let's actually factor out the a's. So we've got on that side mass 2 plus mass 1 times a. I just factor the a's out. Basic algebra. So I've got the a's factored out, so we can divide the other side now by mass 2 plus mass 1. So A equals all that stuff, mass 1g minus mass 2g sine 50 over mass 2 plus mass 1. If you look at that closely, it's just Newton's second law, right? Acceleration equals the sum of the forces over the sum of the mass, over the, sum of the masses. So the mass put together, mass 2 plus mass 1. The sum of the forces over the mass equals the acceleration. Newton's second law. You can double check it, I'll put your numbers in there. But answer should be 9.23. And it's the calculator rate system positive. So we got it exactly right. Find the tension of the string. I erased the tension equations, but you should have the tension equation somewhere. You just plug in the acceleration to your tension equation, and it would be that exactly. So I'm not going to work that out because you should be able to do it yourselves, but that's the idea. So the main idea here is just to know how to approach an Atwood's type problem, an Atwood's machine problem, and yeah, not too complicated. Next question. So here's one we've done together in this exact format. So you should be very familiar with this one, very comfortable with it. And you actually had an exam on this, what, 2 weeks ago? 1 week ago? So I expect you to be able to do this one with relative ease, right? So we got the arm in the figure below where it's 40 newtons. I've changed the numbers a little bit. 40 newtons, the force of gravity acting on the arm acts through point A, as you can see on the diagram. Determines the magnitude of the tension force, force T in the deltoid, and the force that's exerted by the shoulder on the humerus. Hold the arm in the position below like this. So yeah, very much something you're familiar with. We don't have to write anything out, we've got it all here on the diagram. So we know torque equals the radius times force times sine and theta. And we know that the arm is in equilibrium. So that means the torques are canceling each other out. So some of the torques should be 0 here. Some of the torque is 0, some of the forces is also 0. So some of the force is 0 as well. And I have given you everything you need to know. What is the idea with torques and forces? What forces can we disregard? So any force acting on the hinge or the axis point, we're going to say provides no torque. So here, the force S, which is acting on the hinge or the, origin, is going to have no torque. So we've got, let's say some of the torque equals 0. We've got force T providing torque, so we've got 0.10, which is the R. Let's actually write this out. R, that's sine theta. The force is going to be what we're looking for. Sine theta, sine theta is going to be 12, or theta is going to be 12 rather. And that is going, so with torques, right? Counterclockwise is the positive direction, and clockwise is the negative direction. We're going to provide a force that provides a looks like it's going to be counterclockwise torque, right? So positive. The next force, the weight, force G, is going to provide a negative torque, right? So we're going to minus R, which is 0.4, times the force, which is just going to be the mass times gravity, or actually they gave it to us, right? 40 newtons. And then it's going straight down, so sine 90 is going to be 1, right? So we've got 0.1 times force T times sine 12 minus 0.4 times 40 should give us 0, right? We just move the 0.4 times 40 over. So 0.4 times 40 is going to be 16. 0.10 times force T times sine 12 equals 16. 16 divided by 0.1, it's going to be 160. And then 160 divided by sine 12, it's going to be 769.56. So force T is going to be 769.56 newtons. And I'll just show you all I'm at there. Sort of scattered, I actually ran through that a bit. But you guys should be very familiar with this one, so I don't want to spend too much time on it. But just know it's very important. I feel like people will definitely need to be familiar with this. This concept is very important. So force T is going to be 769.56. We also want to know the force Fs. So we've got force T, we want to find force S now. Let's just switch markers. So force S. Some of the forces, or some of the torque is 0, so I told you as well, some of the forces is 0 by that same standard. We've got three forces. They're acting in both the X and Y direction, right? We know we gotta keep our X and Y separate, right? So we've got, let's do this. Some of the forces in the X is 0. Some of the forces in the Y is also 0. Let's focus on the X's first, right? So, X direction, we've got force T acting in X direction, we've got force S acting in X direction. They're actually going in opposite directions, so we can go ahead and just put equal to each other, right? So force T, X component, is going to be force T times the sine or cosine of 12, do we think? If you said cosine of 12, exactly right. So force T cosine of 12 is going to be our first X force. Our X component of force S is going to be, let's actually just say force S, X. We're going to do a little bit of an easier method for this. Actually, I showed you this method earlier. As opposed to finding the angles, we're just going to do force SX. So the X component of force S should give us $752.74. So force SX is 752.74 newtons. So if you're at that, the X component of force S is 752.74. We want the Y component now, right? So we've got three forces acting in the Y component. We've got force SY going down. We've got weight going down. And we've got force T going up. So we've got force T sine or cosine of 12. You said sine, you're exactly right. So we've got positive force T sine of 12. We've got minus force SY, right? the y component of force S. We've also got minus force G, which is the weight. So we've got minus the weight. What does that equal? 0, right? So here's what I've got. And you want to solve for force Sy, right? We just move that over. We just move that over. So force Sy, or the y component of force S, should be force T sine 12 minus the weight, and that would be the force Sy. So force T again is 769.56 times sine 12. And we're also going to subtract the 40 for the weight. And for force Sy, I'm getting 120 newtons. So they've got an x and y component. And actually, you can look at the diagram and see what I'm going to tell you to do, right? Little triangle work, little Pythagorean theorem, little little trig, and you should be able to get your magnitude, and they don't need the direction, but fine as well if you wanted to. So that's the idea. I'm not going to work it out because it's pretty simple in that regard. You've done it a million times this past few weeks, so that's it. Make sure you know how to do these, and let's move on to the next one. So here we're back to the new stuff, right? And you guys should be experts on this. It's going to be a good part of your exam. So I'm not actually going to show you how to do these. I'm not actually going to show you how to do this. But I will give you some leading questions. I will give you some good ideas, right? At the steam at 100 degrees, at ice at 0 degrees, by the amount of ice melted and the final temperature when the mass of steam is 20 grams and the mass of ice is 120 grams. So questions, right? We've got what happening here. If we drew it out, we've got the ice interacting with the steam. Ice is going to melt, steam is going to condense, in theory, right? So ice makes some water, steam makes some water. Boom, that's it. That's it, right? So here, like, it seems like we could find, or we could always find, how much energy we need to melt the ice and how much energy the steam releases when it condenses. So, two things, right? How much energy do we need to melt the ice, and how much energy will the steam release once it condenses? So, I'm not going to write that up, but consider that. How much energy do we need to melt the ice? How much energy will the steam release once it condenses? We've got that. So you should find, let me actually do the math really quickly. And then you should find that you have enough energy for the steam to melt all of the ice. So that's the case. You've got exactly what I have here. You've got the steam condensing in total. You've got the ice condensing, or ice melting in total. You're going to make 2 puddles of water essentially, so you've got 2 masses of water. So you've got 2 phase changes and 2 temperature changes. Ice changes the water, that water changes temperature. Steam changes the water, that water changes temperature. So you've got sort of an equilibrium equation. You've got all your Q's together. And they're going to come to equilibrium. So the idea is at that equilibrium point you can find temperature, right? First Q is for the phase change. So ice is going to change to water, positive phase change. So you're just going to use whatever you need to use. Just figure it out yourself. You should know. We can also say that the second phase or second Q is going to be the temperature change of that water. So it's going to go from 0 degrees to whatever its new temperature is. So the temperature change. Next, we've got the steam condensing, right? So steam condenses, it's going to give away energy. It's going to have a negative energy. and you can find however you need to find how much energy the steam releases when it condenses. As steam condenses turns to water, that water is going to change temperature to whatever its new temperature is. So from 100 degrees to whatever its new temperature is, right? That's the idea. So I already gave you all the information you need. You're going to melt all the ice in this scenario, and you're going to find your temperature with an equilibrium equation. So that's that. If you have any questions, email me or Espino or Daniel. We're shooting pros here, so let's get to the next one. Same idea here. Steam at 100 degrees adds ice at 0 degrees. Of course, amount of ice melted and the temperature when the mass of steam is 5 grams, and the mass of ice is 67 grams. So similar approach, right? You have the mass of the steam, you have the mass of the ice. You could initially find if you can melt all the ice with that amount of steam. You can't melt all that ice with that steam. So you're going to see you're going to have ice left over. You have ice left over. What does that mean? Ice at 0 degrees is left over. What does that mean about the temperature? So consider that. You also want to find the mass of the ice left over. You have the energy needed to melt the ice, or not energy needed to melt the ice, but you have, well, yes you do, you could find that. It doesn't matter, actually. So you've got the energy presented by the steam when it condenses, and you've got the energy when that steam changes temperature to 0 degrees, right? So you've got energy that the steam releases, and you've got the energy that is released once that steam changes temperature. So it goes from 100 to whatever, or goes to 100 to 0 actually. That's losing a lot of heat, right? So in that scenario, you've got two energies or two Qs being provided. With that energy you find, that the sum of those two energies, we go ahead and say that we've got this energy, we've got this value, we want to know what the mass is, right? So you can use your energy and your mass, or you don't have a mass, but you can use your energy and another value to find the mass, right? So consider that. I really gave you like the gist of that, but I think maybe it wasn't worded the best. But familiarize yourself with the formula sheet. You should be pros with this problem again. And I actually solved this just in my last video, so if you're not familiar with this idea, go to the last video or email me or Espino. That's it. So make sure you can do this. Make sure you can do number 6 as well. But that is the meat. This is the meat, if you ask me, of section 4. So definitely familiarize yourself with these concepts. So similar to the last few, we saw this in the last video, so I'm not going to do it. You should be familiar with it, and once you guys be able to do these by yourself, we should be able to do at this point. So we've got a gas increasing 3 atmospheres to 9 atmospheres, blah, blah. So exactly what you see in the picture or diagram. 3 to 9, 1 to 3. You know that work is pressure times volume, or change volume, and that's going to be actually on your formula sheet as well. The idea here, I always say you just want to treat this as if you find the area of whatever shape you have. Here you got a triangle. So area of a triangle, what's that going to be? So consider that you're going to find the area of that triangle. And actually, if I'm looking at this, it's not the toughest, but make sure you can do this. Make sure you can do this. If you can read these diagrams, you can solve for the work, you're good. And it's actually exactly actually it's in atmospheres times cubic meters. You want your pressure to be in pascals, so know your conversion rate. I'm sure Espino actually give it to you in pascals if you need one of these, but consider that as well. And beyond that, not too tough. Not the toughest problem, but I do want you to be able to solve these with no difficulty. So that's it. So this is the last video for my SIs, and this is my last SI period. Crazy to think about. I got up early for this one. Like the sun's still out. Usually the sun's gone by the time I finish these. Got up early, figured I'd knock this out, give you some good information. Final exam should be what? next week, maybe the week after. Got a little information I wanted to share with you guys about just what to expect based on the last few finals. Everything on here, good information, of course. So last year, there was definitely a collision in 2D motion, which we touched a little bit. 2D collision, projectile motion, which we didn't exactly touch, but we touched. I guess maybe we touched projectile motion with. I guess that was number 3, maybe number 2, with the rocket and the airplane. Make sure you know your quadratic formula because that will come back and bite you essentially. But make sure you practice your quadratic formula. Atwood's machine problems are a constant staple. Make sure you know your Atwood's machine problems. Probably going to be on there. The arm torque type problems, so the torque with the arm, or maybe like we've got like a string holding, or actually rope holding the bar, or something like that. Essentially on there. But yeah, those are the main ideas. I think last year you did chapter 4, or actually section 4 is about 40% of the test. So make sure you're really familiar with section 4. Make sure that's what you're reviewing mostly, maybe not mostly, but make sure you're familiar with that. The other stuff you should be able to do at this point. Like, it all builds on each other, or it all builds on itself. So ideally, you've been focusing, you've been paying attention, and now you know everything, right? In theory, right? It's been a great year, it's been a pleasure, but happy to wrap it up and graduating soon, so it's been real, of course. Feel free to always email me, emails being Daniel. But email me especially because I do like to help you guys, and I'm happy to be here for you. But that's it. Signing off for the last time. Enjoy your break.